Good afternoon, everyone. My name is Mr. Shrego, and today I am going to be talking to you about color by addition, color by subtraction, and color filters, all the really key things that are built into our Unit 5 about light, color, and like everything. I mean, honestly, everything we see around us is colorful, and like this is how your phone makes colors on the screen. This is how the smartboard is making black, white, and any other color we might see on here. It's why all the dots on my shirt are different colors. Which, yeah, I'm wearing this shirt specifically because it's color day. So let's start off. Color by addition. Color by addition is a thing that is only really used when we're talking about things that emit light. So good examples of this, right, are our projectors. Those emit light, right? They are generators of light. And computer screens, phone screens, tons of stuff that we see around us in our lives that are colorful and emitting light work on color by addition. When you mix different colors of light, they add up and they make new colors. By mixing those different colors in different amounts, we're able to get all of the different wonderful colors that you are seeing on the screen right now while you watch this, or on your phone when you're texting a friend or snapping them or whatever you're doing these days. Sounding like an old person. Now, the primary colors of light, for some of you, you're going to be a little surprised by this because you're used to working in the world of art or more of the other realm of color by subtraction. That's later. But turns out if you're working with computer art or you've been doing things with computer science, you might be familiar with the fact that the primary colors of light for color by addition are just red, green, and blue. By mixing these colors in different amounts, like different brightnesses of blue versus red versus green, you can get all the colors of the rainbow, which is just really, really freaking cool. Now, when I take some of those colors and just add fully like a bright red light source and a bright green light source, we get what are called secondary colors. They're when we add red and green or green and blue or red and blue equally. Now, the way that happens is for secondary colors of light, if we add red and green, we get yellow. Now, if you've had a chance to do some of the light stations, you might be familiar with this because you maybe tried playing around with the colored flashlights and were able to see that when you shone those colors together, they added up to give you a yellowish color. Depends on how intense each of them was. Now, if we move on, we can go and say like, all right, well, what happens if we mix green and blue? Well, if we mix green and blue, we kind of get a color that's kind of not quite green, not quite blue. You might be familiar with it as cyan, a color that I quite like. It's really beautiful. Now, the last one we get is, well, all three, the three different combinations. We can add red and blue together. That's going to give us magenta. It's kind of a purplish color. It's also quite pleasant. What's kind of fun is that you see this a lot in electronics and certain small devices where there will be an LED built into it somewhere that it has a tiny little red light, tiny little green light, and a tiny little blue light. And they'll use that to generate all of these different colors of indication to like tell you different things about what the device is doing. Also interesting is that for a lot of our phone screens, they're what are called OLED screens. They're actually tiny, like giant, just arrays of tiny, tiny, tiny little LEDs, tiny little lights. And those tiny little lights are what are making the image you see on your phone. When they change color, it's just changing how bright the red, green, or blue lights are to give you different colors of light. So again, when we add red and green, we get yellow. When we add green and blue, we get cyan. When we add red and blue, we get a nice, lovely magenta. All just absolutely beautiful colors that I really like. Oh no, I need to click back onto this. Excuse me for one moment. By now, you're all looking forward to when the world returns to a little bit more normal and we can stop learning like this. Maybe you like this. I kind of like having the videos available to you. For instance, we added combinations of two, but what if we add all three together, right? If we add red and green and blue, Actually, turns out this gives us something pretty darn close to white light. Right? It's a lot of people aren't comfortable with this until they try it. So I encourage you, when you're in class, go to that wave station where you're able to shine all those lights. Shine them all together. You're going to get a color pretty close to white. And if those flashlights were all the exact same intensity, you'd get a color that's like it's white. It looks like white light. But that's not the only thing we deal with here in the world, right? Not everything we see emits light. A lot of things actually reflect light. And so the things that we see in the world that reflect light operate on color by subtraction. With color by subtraction, oh boy, I jumped way far away from this. That's my bad. I wonder what button I pressed. C'est la vie. All right. So let's talk color by subtraction. When you mix different colors of pigment together, they take away colors to make new colors. Pigments are what you see, or what give our, like any of our things that have color in life, that's what gives them that color. They're chemicals that will only reflect certain colors of light. For this, we actually flip our primary colors of light and secondary colors of light. For color by subtraction, and you might be familiar with this more from the art world or from the world of like having to print things on your printer or buy ink for your printer. One of those cartridges of ink has cyan ink in it, magenta ink in it, and yellow ink. Now, if you're thinking back to color by addition, each of one of those, when color with color by addition, was made up of two colors. And those two colors, well, they all end up being our color by subtraction secondary colors. So our secondary colors end up being red, green, and blue. I know it's a little weird that they flip like that, but once we start to play around with this and learn a little bit more about the different colors, I think it's going to all become really clear. So we need to talk a little bit about what happens when we add together some of those colors. It's kind of like what happens if we mix different colors, right? Like mixing paints and mixing other things. It's not going to behave exactly the same as mixing paint, but it's pretty darn close. Turns out there's a lot more science that goes into art and like the science of pigments and art materials that I hope you all enjoy diving deeper into at some point in your life. For today, we're going to talk a little bit about what happens when we mix our primary colors by subtraction. For instance, magenta, well, magenta is made up of red and blue. Now, cyan is made up of green and blue. If we mix these together, well, what magenta does, magenta essentially will only reflect green or red and blue light. What happens is if you have a magenta object, that magenta object is absorbing all the light that isn't red or blue, and it's only re-emitting kind of light that's going to end up looking like magenta. So what we lose here is we lost green light with our magenta pigment. The way you can kind of deal with figuring out these little problems here is look at, well, okay, magenta is made up of red and blue originally in color by addition. So if white light, which white light was made up of red, green, and blue, that shines on a magenta object, that magenta object absorbs green and reflects red and blue. Our cyan object absorbs red because it's made up of green and blue. So if we mix those two colors together, we'll get a pigment or a paint or something that subtracts any green light that hits it away and subtracts any red light that hits it away, making it blue. Now we can use this same idea to figure out the rest of these, right? Red and green made up yellow originally, and the magenta remains red plus blue. Red and green, that subtracts blue. Red and blue, that subtracts green. If we take white light made up of red, green, and blue, subtract blue, subtract green, we're only left with red. Same process for cyan and yellow. Cyan light is made up of green and blue. Yellow is made up of red and green. So green and blue, subtract red. Red and green, subtract blue. And so if we take red, green, and blue, our white light, we subtract the red, we subtract the blue, we're left with green. Now, if we move on down here, we can kind of follow the same idea. Cyan is a pigment that takes red light away and absorbs it. Yellow took blue light away and absorbed it. And magenta took green light away and absorbed it. So if we take white light made up of red, greens, and blues, we subtract away the red, green, and blue, we get nothing. It's blackness, it's dark, there's no light. And you can kind of think about the outline, the blacker parts of my shirt as doing that, right? Everything on this shirt here is working by color by subtraction, right? Our red circle right here, right, is taking that white light, and that red circle is subtracting away the green light. Oops, sorry, it's subtracting away our green light and it's subtracting away our blue light to give us the red light for this circle, right? All of these things on here are made up of that. And you can see some of them really look like true pigments and some of them aren't quite like that. In class, we'll hopefully be taking a look at these where we're gonna shine the different colors of lights onto these shirts and watch as some of these dots disappear. Unfortunately, it's COVID. I don't have a helper with me in here because I'm not gonna do the video masked. It's a lot harder to talk to you that way. And so we're just not gonna be doing that right now. It is a really cool demo and I'm hoping your teacher's gonna show you in class. It doesn't come across on camera the same way it does in person. Cameras are a little too smart for this. All right, I got to go to my mouse. So as we're going on, we're going to get to this next page. This is page 18. And we need to talk a little bit more about what's called a color filter. Color filters are also another thing that operate by color by subtraction. Instead of absorbing and reflecting light, however, they're only designed to just absorb some light and let the rest of the light pass through. For people who live in the world of theater, you might be familiar with these as gels or things that you put over your white light sources in the theater to make all of the beautiful colors that let your plays be so freaking awesome. I've always been impressed with the quality of our plays here. So we've got red, blue, and green light. White light, that is. It's coming up towards our cyan filter, and cyan was made up of green plus blue. Now, I like to think of our color filters kind of the way I think about a coffee filter. A coffee filter, you put your grounds in there, you pour your water in, and the only thing that comes out the other side is coffee, right? The name of the filter is what it lets through. In this case, our cyan filter only lets through cyan. And so here, our green light would pass through that comfortably. Our blue light would also pass through that comfortably. Our red light doesn't though, because red light isn't part of cyan. It's the coffee grounds. It's part of the light, but it's not part that we want in our final product. That's how color filters work. Let's take a look more. You know, it scrolls a little too much with my clicker. Shame. Oh well, you can just fast forward the slow parts of this video. I'm really hoping you do that. White light passes through the filters below. We got to label the arrows on the diagram with the colors that go through each filter. Well, again, filters only let through what's in the name. A magenta filter is going to filter out everything that's not red or blue. Right? It's a filter that only lets magenta through. So that doesn't allow green through. We get red. We get blue. And then that red and blue, they approach the yellow filter. Well, the yellow filter only lets yellow through, right? Red and green make up yellow. Now, filter's not going to magically make an ingredient appear, right? If I take a coffee filter and I load up, you know, coffee, but I don't put the water in, it's not like water is going to show up like magic. Instead, what's going to happen, right? Our yellow filter will let through anything that is a component of yellow. So red light passes through just fine, but since blue isn't a component of yellow, the blue light gets stopped. Not too bad. You should expect diagrams like this in your future, or like questions about this perhaps when we get to an assessment. This next one in particular, I happen to always like because, looking at a shirt that is a certain color, that is a thing we do. And when you're in class, I encourage you, get your teacher to turn the lights down low, wear a shirt that's kind of like one of these colors, and go start shining our colored flashlights on it. And you're going to start seeing that some of these things don't look quite like you expected them to anymore. And it just doesn't show up on the camera. I encourage you, try these guys out in person. You will be pleased with some of the results. All right, our yellow filter. That's a filter that only allows red and green through. Stops that blue. Red and green then go and they hit our cyan shirt and they reflect off of that, right? The cyan shirt is going to absorb any color that's not part of cyan. Cyan is green and blue. And again, we don't have blue light coming in, so it's not going to be able to reflect something that isn't there. So our red light hits here. Ooh, red light's not a part of cyan. That gets eaten up by the shirt. And only green light is going to get reflected off the shirt. Kind of like this is how all of this stuff in our lives really works in terms of seeing colors. If you're looking at the whiteboard, think about the fact that all of the different color markers we are using have different materials in them because those different materials absorb light differently. Now, that'll move you on to the formative assessment, but I hope at least our notes today were helpful to you in getting started with that formative assessment. Thanks for stopping in.